Morning, everybody. Morning, Donnie. Morning, Charlie. Morning, Hike. Morning, Ava. Hi, Azra. Hi, Ryan. Hi, Kim. Good seeing you. So, today, in the agenda, we're going to work on DNA number 4. 4 on a Monday because we are continuing from last week. The same sheet. Nice, long DNA sheet. So today we're going to do, for May 11th, DNA number 4. Morning, Kim. I miss killed off. Well, I'm not a mother, so. It was good. Hoping yours was too. So we're doing, for May 11th, DNA number 4. You're continuing this same sheet, 26. Alright. And DNA number 4 is, what is a star? I asked this question at the beginning of when we started doing space. I want to see if you can add anything more to what you put. So as you're kind of thinking about this answer, about what a star is, maybe think about some of the types. This right here is a snapshot of the local neighborhood in the Milky Way galaxy. A galaxy is a collection of millions to billions to even some galaxies, trillions of stars. So this is not an actual image, obviously. We can't look at the Milky Way because we've only barely left the solar system. All of these are stars. And as we've found out in our GSA, most stars have planets. So if you're looking at about 300 billion stars in the Milky Way galaxy, you're looking at trillions of planets across the galaxy. So galaxy is a collection of stars, all held together by gravity. We'll get more into gravity after this next topic of stars and what's at the center of the Milky Way galaxy. But if I zoom back in, are all stars the same? While you're writing your answer, I'm going to provide you 3 criteria I want you to think about when you're looking at a star. 3 major differences. Hopefully you've heard of maybe some of these stars kind of in the nearby neighborhood. Vega, very bright star. Going to be our future North Star in a few thousand years. Pollux makes up 1/2 of the constellation Gemini, with the other star Castor. Sirius, one of the brightest stars in the night sky. You can find it by using Orion's belt as an arrow pointing backwards. Pyramids of Giza were modeled after Orion's belt, and Sirius, I forget if there was a tomb there or the Sphinx. Oh, maybe Mr. Howman or Social Studies nuts might know better. Anything else? Oh, there's Castor. So Castor and Pollux are in the same constellation, but they're not in the same area, which is always very interesting. Stars don't have to be in the same location to be in a constellation. And then there's our sun. Those of you who were doing APC last week, Alpha and Proxima Centauri, we used to think they were one star, but then we found out they were binary. And that would be our star, I imagine. So that was Proxima Centauri. Let's take a look at another one. Let's take a look at Sirius. So again, if you joined late, hi Rain. How you doing, Nikolai? We're asking the question in the DNA, what is a star? And you're kind of typing out an answer. And I asked this earlier in the unit, way in the beginning, but see if you can add on to it now, based on what we've done last week and the weeks prior. And also take a look at this Chrome web app, stars.chromeexperiments.com. Taking a look at some stars in the nearby galactic neighborhood to see if there are differences between some of these stars that we can figure out. We'll zoom it out a little further. I was looking for Betelgeuse, but I think it's too far away and the font too small to find it easy. Some of the stars in the Big and Little Dipper. Whoa. A little too close. It's a big star. Alright, so DNA number 4. What is a star? I would say, and this kind of came from our previous answer in the beginning of the unit, a star is a massive collection of gas that undergoes fusion at the core due to gravitational pressure. Isn't a star a massive ball of gas? Yeah. It's a massive collection of gas that undergoes fusion at the core due to gravitational pressure. Alright, Earth, Jupiter, they don't have fusion at the core. They're not taking atoms, combining them together, and releasing energy. Not making sunlight. But our sun is, and other stars are. And I'd say there are 3 criteria to look at to classify them. Two and three would kind of be related. I'd say first, the biggest thing that we can literally look at in terms of difference is going to be, if you remember, looking back at this star and then something like Proxima Centauri, a red dwarf, a yellow giant. Well, I'd say size. So we can classify a star based on size. Right? And then a red dwarf versus a yellow giant versus something like, I think we clicked on Sirius and that was blue. So red, blue, yellow. There's different colors. So there's different sizes and there's different colors. So I delete that S. Size, color. And if they have different colors, so this kind of relates. If they have different colors, then that means they must have different temperatures. Why? Think of like a campfire. Blue fire versus the orange fire versus the yellow part of a fire. What part of the fire is the hottest part? Is it the blue or is it the yellow part? So, size, color, and then temperature. Size and color can kind of be used together too to determine brightness. You'd also need distance, but you know what, forget it. I'm just going to use those three. Size, color, and temperature. So we have something like a red dwarf, like Proxima Centauri. You have our sun. And then something like even get rid of me for a second. It was in the news a lot recently because it looked like it was dimming, which meant it was near the end of its life. Betelgeuse in the constellation Orion is a red supergiant. So stars have lots of differences in appearances, just like planets. I know in the beginning of the unit we had this question about what is a star, but for this question, number 4, on May 11th, just add a little more detail based on kind of what we've heard or researched, and just taking a look around our galaxy. Galaxies, again, collections of billions to trillions of stars. Different shapes, too. Not all of them are spirals, but we won't have a lot of time to go into them. Alright, so here is DNA number 4. We'll have 2 more, Tuesday and Wednesday, review Thursday, and take DNAC XL 26 for our 26th sheet. So what's next? Your sheet's due Wednesday before midnight, and so too is seeing stars. Seeing stars is the next thing we're going to work on, the next topic being looking at different types, different classifications of stars. Because we've done solar systems, or our solar system, we've looked at exoplanets, and how about the stars that those planets go around? So I would open up seeing stars. We're going to go through the explore section today, together. Alright, just read through what I've typed out, what I've brought together, and then you guys are going to answer 1 through 5 in the explain section. Alright, so today we'll read through the explore, we'll do the explain section. Tomorrow we'll review those answers. You'll open up Star in a Box, and you're actually going to look at stars twice as massive as our sun, 40 times as massive as our sun, see what happens to those different types of stars in terms of their stages of their life. So you'll be filling out this table, temperature, luminosity, size, based on Star in a Box. And then there's an evaluate at the end. Alright? So we're going to read through together the explore section, and you're going to do the explain. Let me zoom out a hair. There. Alright. Look back. Start the explore section. In the beginning of the school year, we reviewed 3 types of heat transfer: conduction, convection, and then radiation. Heat is the transfer of thermal energy of a substance or object, right? Therefore, these 3 types of heat transfer are still ways to transfer and conserve energy in general. Throughout the first and second trimester, these 3 ways to transfer energy came up in the water cycle, in weather, climate change, and now we're going to kind of round it out with astronomy and light. And so this right here being the basis for radiation. This is fusion. This is 2 protons coming together to form helium. Protons, just 1 proton in an atom of hydrogen. So 2 hydrogens come together to make 1 atom of helium, and that releases energy. Alright? The transfer of energy through electromagnetic waves or light is radiation, but energy has to come from something else. So how does our sun and other stars actually radiate light? So where does the material and the energy for fusion to come from in a star? In situations of extremely high temperature and pressure due to the attractive force of gravity, matter wanting to pull on other matter, atoms can combine during the process of nuclear fusion to become one larger atom. This process results in a tremendous release of energy. Nuclear fusion occurs in the cores of stars. The light we see is the release of the resulting energy. This energy causes a star to expand outward in all directions. So fusion is actually trying to blow the star apart. But most of the time this doesn't happen. Why not? Matter is attracted to other matter on a macro, or macro meaning large, micro like a microscope means small, scale by the force known as gravity. On Earth you feel it as a downward force. In actuality, gravity works in all directions, pulling towards the center, right? That's why you get spheres out in space. So, in a star, fusion is occurring due to gravity, but at the same time, fusion's pressing out and gravity's pulling in. There is a fine balance between gravitational attraction and fusion energy. This is called equilibrium. The two forces are equal, right? Without it, a star would change. So at different parts of different stars' lives, some forces take control more than the other. And that's how you get a star that changes its size over its life cycle. Our sun is going to become larger. Something's going to happen at the core as our star gets older. All right? The Earth's gravity is trying to pull you and the objects around you to the Earth's center. Gravity is what provides the pressure needed to squeeze hydrogen with other hydrogen atoms to create helium in fusion. The more mass a star has, then the more gravity it has. This allows it to conduct more fusion. It also forces larger stars to use up their hydrogen fuel faster. That forces them to go through the stellar life cycle faster as well. So this introduced the idea that stars go through a life cycle. They're small, they're big, they have different colors, part of their life cycle. They're not all going to go through the same life cycle, but they will go through some kind of cycle. This is due to how much mass they have, how much gas is available in the star. Larger stars conduct fusion faster, so they go through the cycle faster. Our sun, it'll take another 5 billion years to finish its fuel based on its size. So it would probably be around for about 10 to 12 billion years total. So now we have 5 questions, and they explain. Can you put fusion in your own words? What is fusion? I kind of mentioned it up here. Can you provide a summary? Or could you also provide an analogy that helps you remember? Some kind of analogy, some kind of, I would also say a connection is also acceptable here. An analogy is some kind of connection that helps you remember what fusion is in your own words. Number 2, what's gravity in your own words? Can you again provide an analogy or some kind of connection? Connections are acceptable. They don't have to be academic connections either. Some kind of connection that helps you remember in your own words what gravity is. So very similar to doing your key term guide back when we were still in school. So number 1, fusion in your own words. Number 2, gravity in your own words. 3, how does fusion and gravity provide a stable star? I would go back to this part right here. Maybe use this diagram to help you explain it. Or go back to the last section. 4 and 5 are kind of extend questions without an extend. I kind of throw at you a picture of Orion. So this is the constellation Orion. Constellations are groupings of stars that we see from our point of view on the Earth to help us better locate those stars. So these stars are not near each other in space. Some of these stars are closer, some of them are further, but from our point of view, they form this pattern. So they form a 2D pattern on the night sky. But remember, these are 3D things and 3D spaces that we're talking about. So here's the constellation Orion to the right. You got the belt here. The 3 stars I'm having you look at are Betelgeuse, which is A, right here, the armpit. Mintaka, B, is in Orion's belt. And then C is Rigel, down here, the ankle. So Orion the hunter, the belt, 2 shoulders, 2 ankles, and really the head kind of extends off the picture, and then he's holding a bow out here, off picture, and he's holding a club above his head up here. But This is pretty much what you're going to find easy in space. You're going to find like this rectangular pattern, and you're going to find the belt. Orion comes up in the fall and the winter, so I don't think you'll be able to see him anymore now. Used to be able to see him in the beginning of spring with Venus, but using this picture now, how do the appearance of stars A, Betelgeuse, B, Mintaka, and C, Rigel compare? So use your DNA today. How do they compare? Size, color, temperature. You can't really determine the temperature, but maybe brightness, size, color, and brightness. So you are describing A, you're describing B, you're describing C. In terms of size, color, brightness. 5. What are some ways the stars in this photo could be grouped or classified? Again, I'm kind of leading you towards the DNA answer today. So 1, 2, and 3 are kind of in your own words, going back to the reading, and then 4 and 5 are what you think, based on the DNA. How can we describe and then classify Betelgeuse, Mintaka, and Rigel, which are 3 stars that make up the constellation Orion? If you have any questions, throw them in chat or send them my way. But hopefully this is straightforward. I was hoping I could search those stars, but it's not letting me. There it is. Pretty much just takes up the entire screen. Gotta zoom way out. This is the star. That is A for 4 and 5. I don't know if I can find the other 2. No, but at least you get to see Betelgeuse. Computer-wise, anyway. Whoops. Didn't mean for that to happen. we will do the extend tomorrow. If you have no questions, we'll work on that tomorrow. Make sure your DNA sheet's up to date. If you have questions while you work, let me know. I'll help you out. Number 3. Fusion versus gravity. How do they provide a star that doesn't blow up or crush down into a black hole? The two forces must be perfectly balanced, like all things should be. Force of gravity, force of fusion need to be at equilibrium. Well, they need to be at equilibrium. Yes. If they are not equal, the star will blow up, or the star will crush down. Depending on the size. More mass means more gravity. But because of that, the more mass means the more fusion needs to happen. So gravity fuels fusion, but they are at equal forces, which prevents the star from being destroyed. Sounds good, Ryan. I am going to end the stream because that was the only question. Anyway. So, DNA number 4, make sure that's taken care of. Do the explain section of seeing stars. And then we'll go over those questions tomorrow. Alright? Have a good Monday. Bye, Azra. Bye, Downey. Bye, Ava. See you, Hike.